So non-ideality of solutions has some interesting consequences, and two that we'll look at here are azeotropes and immiscible phases. So let me recapitulate the fractional distillation slide that we talked about in the context of an ideal solution. So when we mix 1-propanol and 2-propanol, N-propanol and isopropanol, it is possible, as was discussed in video 10.5, to fractionally distill out the higher volatility or lower boiling point component, in this case isopropanol. So remember, we had this boiling point as a function of composition, and as we go up a distillation column to a distillation head and the temperature is dropping, the vapor is condensing, re-vaporizing with more of the more volatile component in the vapor until finally you have nice, pure, most volatile at the very top, and it starts dribbling over into a collection vessel. And that was fractional distillation. So here's a non-ideal solution. This is benzene mixed with ethanol, and this diagram is for, again, atmospheric pressure. And what you see is kind of unusual behavior. So here's the boiling point as a function of composition. So pure benzene boils at about 80 degrees Celsius, and pure ethanol boils at about 78.5. And yet, when you mix them, you will discover a boiling point that is below either of those two temperatures. The mixture starts bubbling before you get to the lower one, 78.5. Of course, again, we can ask questions about what is the mole fraction of a given substance in the vapor above that boiling liquid, and it will continue to follow Dalton's and Raoult's laws in the limit as one of these things gets pure. So were we to have nearly pure 2, we'd expect Y2 to be approaching Raoult's law behavior. But as we get further away, in this case I'm going to take ethanol, I guess, as component 2. So now my mole fraction of ethanol is dropping. Well, now my mole fraction in the gas phase, which is still going to be dictated by Dalton's rule, it's the partial pressure over 760, it's going to approach x2 times Henry's constant, not times the pure vapor pressure. That change allows this phenomenon to happen. And the deviation from ideality that's here means that you can enrich the vapor in either component depending where you are in the mixture. So let's just look at that with maybe some specifics. So let me think about a benzene-rich mixture, right? I'm going to start with about, that looks like 10% ethanol, 90% benzene. And again, as I follow these lines, it's like I'm moving up a distillation column. So I'm holding about a 74-degree bath, and it's bubbling, and it goes up a bit, and the vapor has this enriched composition in ethanol. There's more ethanol in the vapor. And then it hits some cooler glass, and it becomes liquid, and then the temperature warms up a bit more, and it becomes vapor again, and then it becomes liquid. And finally, I come in to this point F, so I go A, B, C, D, E, F, and at this stage, there's nowhere else to go. The vapor has exactly the same composition as the liquid. If I start from the ethanol-rich mixture, so now it's about 90-10, it looks like. Once more at the somewhat higher temperature, I volatilize. I've got more benzene now in the vapor. It runs into some cooler glass, and it becomes liquid, and it volatilizes again, and now there's still more benzene, but it comes back ultimately to this position F. And so my A, B, C, D, E, F, irrespective of initial composition, ultimately takes me into the azeotropic composition, which here is about 55-45, I guess benzene to ethanol in this case. And at that stage, there's nothing you can do. If I hand you a flask of 55-45 benzene to ethanol, you can boil it all you want, but all you'll do is boil it dry, and the vapor will constantly be 55-45. You cannot distill one away from the other. So I will let you think about whether you can do anything in terms of purification here. It's a quick little self-assessment. And now I'll let you take a look at the explanation. I think this one is pretty clear. You can get away with some things, but once you've gotten to an azeotropic mixture, you're toast. All right, now let's look at a different phenomenon. Azeotropes are an interesting phenomena, and actually, probably the most common azeotrope in human civilization to some extent is ethanol water. So if you've ever thought about buying 100% alcohol for recreational reasons, which I don't recommend by any means, but you'll find you can't get it. You can't get 100%. Well, it's hard to get 100% ethanol. Why is that? So you can find this horrible stuff in liquor stores that's called Everclear, and Everclear is about 95% ethanol. And the reason it's 95% ethanol is that's the azeotrope for ethanol and water. You cannot get more water out of ethanol by distilling. Ethanol's got a lower boiling point, so normally when you purify alcohol, you do it by distillation, and you distill it away from a mix of all sorts of stuff, including water. But at a certain point, once you've hit 95.5, the water keeps coming. So if you really want to get rid of that last 5%, and chemists do, not for recreational purposes, they use it as a solvent, for instance, then you have to find another trick. And those other tricks, there are different approaches you might use. It turns out one is to add some benzene and carry off the water in a benzene water azeotrope, allowing you to have ethanol. But that makes some benzene in the ethanol, and you don't want to drink that. That's a whole different story, isn't it? Okay, well, enough about recreational ethanol. That was another aside. Let's look at a new phenomenon. Let's talk about immiscibility. So imagine I have a composition diagram, like the one shown here, where this is vapor pressure as a function of mole fraction above some solution. Here's Raoult's law behavior, right? Here's positive deviation from Raoult's law behavior. And we had a little self-assessment a while ago showing, increasingly positive deviation. And you can ask, what happens as it gets more and more positive, as the molecules like each other less and less? And so what you find is at these changes, this is actually changing the temperature as opposed to changing substances. So I'm going to cool things. So as I go from a warm temperature T3 to a temperature that I'll call critical, a critical temperature, to T2 to T1, and I have less tendency for the molecules to like one another, I can look at the slopes of these lines. And at T3, at the high temperature, I'm always a positive slope. There's some curvature here, but it's still always positive. But at the critical temperature, I observe an inflection point. And what's an inflection point? It's where the first derivative and the second derivative are both equal to 0. So if you like, the line is rolled over, it has no slope, and moreover, its second derivative is 0. With a temperature below that critical temperature, instead what we observe is the line will go up to a certain point. It will intersect a coexistence curve. This is a coexistence curve not between a vapor and a liquid. There is vapor above the solution. Instead, it's a coexistence curve of two different liquids, each characterized by a different composition. And so the way to read this diagram is that at T2, we would find one solution that is characterized by this much of X2. X2 prime is the mole fraction of 2 in the liquid. And another separate phase, they'd be in contact with some sort of meniscus you might be able to visualize, that is much more enriched in component 2 and has this mole fraction. So the two liquid phases separate one from another, driven by this increasingly positive deviation. So this is quite relevant to the phenomenon of, say, fractional crystallization, where we use cooling temperatures to drive a substance out of solution and often into a solid phase. That would be crystallization. It's really sort of the same idea, although there's a few other wrinkles associated with the solid phase. And so such temperature composition diagrams are often shown in a different way as well. Here is one for water and phenol. And the critical temperature now is, so this is now represented as temperature on an axis and mole fraction on the other axis. And again, there is a coexistence curve. In this case, because temperature is increasing along the axis, as we rise, that's where we find a single liquid phase. And as we cool below the critical or consolate temperature, then we reach a position at which you find two different phases, and they begin to separate, and you can just read what are the mole fraction compositions. Here's an example for water and phenol. This is an actual system. So phenol, which is in some particularly foul-tasting cough syrups and cough drops, for instance, sore throat medications, is not terribly soluble in water. If you heat it up enough, you can make a solution. But as you cool them down, they will start to separate water and phenol, and you find different mixtures of the two in those two different phases. So this is the two-phase region. There is another lever rule associated with this. The textbook actually goes through and derives this in some detail, so I will not attempt to do it here. Again, because if you really need to reduce the numbers, I had 6 moles of this and 3 moles of that. That's useful, but I'd kind of like to focus on the concepts, which are the issues of phase separation associated with non-ideality, right? The fact that the interactions between the molecules are different, pure phase compared to one component with another, is really what causes them at some point to want to go back to their original partners, is a way to think about that. Okay, we are prepared to move on. In the next lecture, we'll talk about regular solutions.